Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's DevOps.com program, brought to you by Techstrong and StackState. My name is Cody J. Brown. I'm the host of Techstrong Learning, and we do have an exciting program ahead. First, I have just a couple of housekeeping notes to cover. First off, today's session is being recorded. So if you miss any of our discussion, or maybe you'd like to rewatch or share with a friend, the on-demand recording will be made available shortly after we conclude our live session today. If you have any questions, we want you to send those in using the Q&A tab, which can be found on the right side of your screen. That's also where you'll find the chat tab, and that's where we want you to get to know your fellow audience members. Maybe let us know from where you are tuning in. And we do have two polls that we will be launching throughout today's program, so keep an eye out for those. And if you navigate to the handout section, you'll see that there are 3 resources there available for download. So feel free to get those onto your device at your own leisure. So onto the topic of our program today, we'll be discussing understanding the Observability Maturity Model. And I'm joined by Lodewijk Bogaerts, co-founder and chief technology officer at StackState. Lodewijk, thank you so much for joining me. I'm going to give you the floor.
Hey, thank you, Cody. So yeah, we're going to be talking about the Observability Maturity Model here. And Cody, is my screen visible now?
It is.
Yes, I am sharing my screen. Great. So let me introduce myself. I'm Lodewijk Bogaerts. I'm the CTO and one of the founders of StackState. And at StackState, we are in the observability space and we're talking to lots and lots of customers. And even before that, I used to be a software architect, DevOps architect, and I used to be very much entrenched in the space and knew all the problems firsthand. And when talking to all these different customers, we found many, many similarities. And from these similarities grew a model. That model is the Observability Maturity Model. Now, this is not the first iteration of that model. We've been evolving it since 2017. And so there's a lot of knowledge that goes into this model. And I think it is really valuable and I would like to share it with you today. So we've done the introduction now, and I'm going to talk about what is our need for the observability maturity in general, and then about the model, and then we're going to wrap up 2 polling questions in between. So let's get started. The need for observability maturity. So we see lots of challenges in IT today in terms of reliability. And one of the challenges that observability really needs to deal with is dynamic IT environments. Not only are environments becoming more dynamic, and with dynamic we mean components are moving out and in, and architectures are changing, and new deploys are happening all the time. But also these environments are becoming more and more complex in terms of lots of different microservices or pods, serverless functions, granular services that are constantly talking to each other in all kinds of complicated ways. And that those 2 facts, the dynamicity and the complexity of these systems, mean that we have different challenges today. And observability is one part of the solution of that, but I think we need to go a little bit further, and that's also something that you will find in the maturity model. So another part of that is that, and that's been around also for a long time, we have a lot of telemetry silos. So we have cloud monitoring when you have, when you're running in AWS, when you're running in Azure, when you're running in Google Cloud, you out of the box get a lot of monitoring. But of course, you also have still your old server monitoring. You might have your Nagios running. There's many different type of monitoring. And what we find actually, like network monitoring and data lakes, when you decide to put everything together, what we found is that companies say they will move everything to the cloud, or they say that they will turn off a certain type of monitoring, but all these things move always a lot slower than anticipated. And what we found, and that's also from research, is that companies of a size with more than 1,000 employees will have at least 10 monitoring tools. And in one example, I know actually we're working with a bank. They actually did a count with a big Excel sheet, and they went cross department, and they found 122 monitoring tools. So when looking at monitoring tools, you find tracing tools, you find all kinds of telemetry gathering. So you have Datadog and you have your Dynatrace, and then there's a big project to put everything into Splunk or a big Elasticsearch. Of course, you have still your cloud monitoring, and that's all on top of these different silos. And then not only do you have, of course, all those monitoring tools all with their own alerting and their own metrics and traces and logs, but you also get a lot of dueling dashboards, and you find that one team is looking at this set of dashboard with this set of tools with this set of monitoring telemetry silos, but another team is working with a different tool and a different telemetry silo and so forth. And trying to bring all that together has been a challenge for a very long time, and data lakes really haven't succeeded in that. Also, that's one key part of this, like putting everything into a data lake. The term data swamp has been used as well. Okay, you have everything in one place, but now you have a lot of data, and how are you going to make sense out of that? And all this leads to poor performance and unnecessary cost. And there's a few challenges around that. So one is alert storms. You have all these different monitoring tools. When one thing goes wrong, all of a sudden, a lot of dashboards flash red. With one customer, I remember talking to them. They had a very, very costly 100 million plus outage. It cost them more than 100 million. This is a very large environment. And it was a very painful problem that basically took down an entire data center. And in that case, basically all their monitoring was flashing red, and they had just no clue where the problem was coming from. Lots of alerts. They knew that there was a problem, but very little clue on where the problem was really coming from. And everybody is panicking. And then you have inefficient troubleshooting. So again, like you might have lots of data, you might have lots of monitoring solutions, but which one are you going to use under what circumstances? And also the amount of engineers that are involved, especially in larger environments where you are dealing with lots of legacy systems. When problems propagate throughout the stack, lots of teams are impacted, and lots of monitoring is alert. There's lots of alerts, and lots of people actually are mobilized, and eventually the amount of people decreases until the root cause is found, and then everybody can go on with their day job. So another problem is that IT alerts are not linked to business impact, and that can go in both directions. With one customer, I remember talking to them, and basically they said that, yeah, we know very well what's going on at the top. So all our APIs are all monitored. We know what's going on at the bottom. All our servers are monitoring. And when there is a problem, we see a lot of alerts at the top, we see a lot of alerts at the bottom, but it's very hard to figure out like which ones of these alerts are really connected to each other. And so when there's an alert within a system that's kind of more at the bottom, more low level, or it might be even a microservice that say, hey, I know something is wrong, it's not immediately clear how that impacts the business. And the effect of that is that users will report on the problem, even though there may already be alerts. So that's a big problem. And then reactive troubleshooting, not proactive prevention. And that's something really that we want to not get into situations where we have to do root cause analysis and figure out stuff as much as possible in this short time spaces as possible. Under high pressure, but we want to, of course, prevent problems. And the question is, how are we going to do that? Now, first of all, let's do a polling question. What is your organization's top business-related goal or IT-related goal for observability? And you have a couple of answers here. Please read through the answers and submit a answer. And Cody, I guess that people are now filling in the answers. And there is the poll. Great. And that's an interesting answer. Improving availability, reducing MTTR is leading. Becoming proactive. Second is sharing first place. Here we go, some more updates. Still same. And so I think we're there. Shared first place between improving availability and reducing MTTR, and becoming proactive instead of reactive. That's very interesting because in terms of performance metrics, we're seeing a lot more of that lately, and there have been a bunch of blog posts about performance outages, or the new type of outages, or performance problems, or the new type of outages. But still, this improving availability and reducing MTTR. I think if we would have taken this poll back in 2017, I think that would have been the top answer as well. And becoming proactive instead of reactive, I think that's also been a problem for many, many years. And there's lots and lots of projects that I have seen, and many have failed, actually. So we're going to have to talk about the problems in how do we actually become proactive. And that's a very interesting topic for many of you. So we're going to use the Observability Maturity Model to talk about this space of observability. And hopefully that makes some sense out of the space, because if I've been in this space for many, many years now, and sometimes if I put my Zen mind, beginner's mind on, and I look at it all, it's very confusing. There's observability, there's AIOps, and there's lots of vendors calling, putting lots of words into the market, and we really have to make sense out of that. And hopefully this model does that for you. So the way we've structured the model is that you have 4 levels. So on level 1, we're talking about monitoring, level 2, observability, level 3, causal observability, and level 4, proactive observability. We're going to go through all 4 levels. And even though there is a line drawn here that follows an almost linear path, what we see is actually, and it's also when we take the assessment with customers on the different levels, we see that companies are always investing in all 4 levels, but not in equal measures. So at the end of the assessment, we can put you at a certain place in the model. Let's say you're at level 2.5 or something like that, but that doesn't mean that you have not already invested in level 4. But as you grow in reliability and customer satisfaction. That's the whole goal of the model. And you will also see that at the end of this presentation, we have taken a survey with, I think, 570 companies, and you will see that the model, as it was actually created by us, actually follows very nicely from the data also. You must be wondering what all these levels are about, so let's jump in. The level 1 is monitoring, and monitoring is simply about answering the question, is the system working? And here we're really talking about availability, reliability of systems. We're talking about traffic light conditions also. So is something working, yes or no, or it's deviating, or it's in a warning state or something like that. Typically, you also find some metrics about, API response times or latencies and these kinds of things. Some saturation and capacity measures. And when I pull up a screen like this, you must probably recognize some of this. So here on the left, you see Nagios, which is, I don't have statistics on that, but if I would place a bet, I would place my bet that Nagios is still the most used monitoring tool on the planet. And it's one of those that it's very hard to get rid of, or everybody wants to do something more modern, but at the same time, the simplicity of the system makes it just a very easy start. But what you end up with is a list, basically unordered. Well, you can put some categories, but a list of red, green, orange, red, green, orange. And in this case, when you look, there's a lot of orange and a lot of red. In fact, I took an operations, an SRE's job. The word SRE wasn't used back then, but I took over his job for a day, and he told me to take a screenshot of Nagios, and he said that if this stuff is on orange and red, it's fine. But if these other alerts go on red, you have a problem and you need to take these actions. And on the right, you see Pingdom. So here we're looking at AIs and testing whether they still work and so forth. And that also gives us some metrics. So at this level, I think this is most understood level. You've got as an input, you got alerts and events, or you get events as an input. So the system is working, yes or no, or my response time of my order management API is higher than usual, and then an alert comes out. The order fulfillment service is down or needs attention, and you get some limited performance insights as well. So 3 reasons why level 1 is not enough, and we need to mature to level 2, which is observability. So first, it tells you something is broken, but does not point you at what, and nor does it tell you who to call. I don't think it needs much explanation. The second is it takes quite some time to create all these alerting rules, and then there's a bunch of dashboarding around that. And I find that actually as a quite high maintenance cost. And the problem here is that if you stay on level 1 and you never mature, you never take the step to go to level 2, 3, or 4, you need to create alerting for basically everything in order to find the root cause. And because the alert is the accuracy of the alert on, like, here's the problem, is going to be very important for you. But in order to do that, you need to create alerts on all levels, and that becomes very costly. And then you have alert storms. So one problem, 25 alerts. This happens a lot. And also duplicate alerts and false positives, very, very common. So we need to mature to level 2, which is observability. And I'm pretty sure that everybody is aware of observability, otherwise you wouldn't be in this webinar. But my colleague told me, like, you should explain observability because it's vaguely defined. And that's, I think, also the first thing. We have our own definition at StackState, but there you can't really go to some type of website and say, hey, what's the definition of, definitively say, what's the definition of observability. There's a bunch of definitions out there, and I don't find all of them as useful, especially the one where you go to Wikipedia and look at the definition of observability as it relates to control theory, because really it doesn't translate very well. And that definition is about determining the state of a system based on its outputs. But in fact, metrics, logs, and traces, the question is, are those outputs or not? But that's really what this centers around. It centers around understanding why a system is not working, and doing that with a combination of metrics, logs, and traces. And I'd rather keep it kind of at that level than try and really capture it a lot stronger than that, because then you get to disqualify a lot of solutions and different approaches that I don't find is super helpful. But what I do find very helpful is, thinking about observability as something that you implement in your applications, or an observability first approach. And a lot of new apps are going to support open telemetry. And I think that really is, a good definition of what observability is coming really from open telemetry and the protobuf bindings that they have. And also, I think observability, like this is one thing to point out, is that observability is really born out of the dynamicity and complexity of systems. Like it really, when you have a pet server with your pet Java applications running on it, then alerting most of the time is good enough, because you have an alert. Okay, something's going wrong. It's my pet application. I know exactly where I should be. I'm going to look in the log. That log doesn't even need to be in Splunk or Elastic or some logging solution. I could just log in to the machine and check out the log, and then there's a stack trace there. Let me just figure out what that is. Okay, this is the problem, and go fix. That's pretty okay-ish. But when you have many different Go based microservices that are communicating to each other with gRPC or some other type of protocol, and Kubernetes is spinning pods up and down, then it becomes pretty tricky to find out what the root cause is and even where to be. And then you need some type of aggregation of quality data, and metrics, logs, and traces give you those. So the metrics tell you kind of the performance of the system at a given point in time. The logs tell you what the system is doing, so you really understand in detail what the system is doing, and the traces tell you something about the performance per request, and that then helps you figure out where performance bottlenecks are. And observability really looks like this. So here you have a Grafana dashboard, and you can drill down into traces, and you can drill down and you can create all kinds of metrics, and so it's very, very fancy. And it can really speed up your troubleshooting process if you have access to this type of observability. So really, observability is an add-on to level 1 monitoring. You still have all your alerting. You need all that. You still have those events that lead to alerts. You also need those dashboards. You still need PIM. Hey, I wouldn't throw Nagios away, and that's typically also what we still see, although maybe in new environments it's not introduced. But now we have elaborate metrics, logs, and traces, so that when something is going wrong, I can do faster troubleshooting. I have these performance insights that help me optimize my customer experience. And I also, and that is really something that is just impossible, but it's very hard at level 1, is it gives me an ability to discover unknown failure modes in addition to known types of failure. So it gives you new types of insights, and I can create alerts out of those metrics, logs, and traces, which previously weren't possible. And I can make smart queries on exactly the type of problem that I foresee happening. And then as an output, you get lots of graphs, gauges, flame charts, logs, etc. But we need to go a little bit further. And here's 3 reasons why. So first of all, again, you have a pretty high maintenance cost, but this time the maintenance cost is really on those dashboards. And those dashboards, they are hit or miss. I know of many teams that actually create dashboard templates for Grafana, and then they generate those. And so, there's ways of it, like with GitOps, you can kind of manage the complexity of dashboards. But dashboards are pretty expensive to maintain and to get right. And with what I mean with hit or miss is, like, if there is an issue, either a dashboard that you have made before the issue even occurs is going to help you or not. And if not, then the option 2 is to do querying. And so in the assessment of the observability maturity model, one of the questions is, how much of the time do custom queries need to be written in the middle of the issue? And I was surprised. I thought that the percentage would be 30 to 40%, but we're finding more. It's in the 60 to 70% of the time. So dashboards aren't really very effective because you make them a priori, then an issue occurs, and then you need very specific context on what's going on. And querying under pressure, is complicated and time consuming. And that's also what we find is that even though we have now sped up the process, it's still time consuming to do all this manual troubleshooting. And you still have to deal with this complex and dynamic system. And although all the metrics, logs, and traces are there, you still have to figure out where to be. And that then creates an over-reliance on super engineers, or what I would call super engineers are people who really know the system. So, what's the difference between, the normal engineer and the super engineer is that super engineer knows the system and therefore knows how to exclude much of the data. They understand, this problem is happening, those microservices. So they know not to look at these other microservices. They know, somebody may change to that really. And that means that they can very quickly exclude data. And then because they know the data, they can write the right queries and get down to the root cause of an issue in the troubleshooting process. But that means that we still have that over-reliance on super engineers, and if that guy or that woman is on holiday, then we have real problems. And so the question is really, how can we make our reliance on those super engineers, how can we lower that? How can we make sure that we give that power to everybody? And level 3 really is about that. And now we get into a new topic, and that's something that we call causal observability. So really here, the question is, what are the causes and effects of the system not working? And when you're just dealing with metrics, logs, and traces, that's sometimes an extremely hard question to answer. So what we found at StackState, and this has been a hypothesis since the beginning of our founding, and also something that we have seen and validated over and over again in the market, is that what you need is an understanding of how your system is put together. And that's what we call the topology. It's that map that describes the relationships between the components. So those components can be microservices, they can be servers, they can be routers, they can be cloud environments, VPCs, it can be anything. So you have those components and they make up some relationships with each other. And those relationships, they actually change over time. And when they change, that is actually a critical moment in time as well, because what we found is that a lot of the problems, and from one survey we found 76% of the time, those problems originate with a change. And so you need to have also the changes. And when I got started in observability or building StackState, we were talking with customers and they said, yeah, we have a CMDB. And in that CMDB, we understand how our system is put together. But what turns out is all of them also told us, yeah, our CMDB is never up to date. A lot of it is manually kept. And so basically, they said that, yeah, we have that CMDB, we're not really using it. And that's really a pity, something that we need to change, because why is that super engineer able to exclude all those metrics, logs, and traces when they're doing a troubleshooting, is because they know where the changes are. And so that makes it possible for them to do that. We can actually automate that by making topology and change first class. And in StackState, that looks like this. So here you can see a topology, and you see in this case it's a lambda, a bunch of lambda functions in AWS, and you can see that we can also time travel over those. And then you can look at the different changes and see what kind of properties changed and so on. And so, why do I feel causal observability is so important? Well, the observability blind spot, and actually just have published a blog on that topic as well, is that more than half of all issues are caused by changes. So it's really funny in a way that observability solutions, which are all about metrics, logs, and changes, traces, don't include changes, and because that's most likely where your root cause is. And so really need a model in which change is a first-class citizen. But change also implies topology. And so when you think about this from first principles, you always get back to the same conclusion, at least we do, is that change implies topology. So change relating to what? And then you get to those components. So a change can be a code deployment, could be a new version relating to an app or to a microservice or to a cloud environment or to a router, a switch, could be a configuration change of your Kubernetes cluster. It could be anything, but it always relates to some discrete component. And when you have those discrete components, the next question about changes is like, I have a business application and I want to know which change in my business application could be the cause of my problem. So now I need to know how my business application or my business service is ran. And it could be, hey, I have a Kubernetes cluster in Azure. It's running on AKS. It has a bunch of APIs. Those APIs are serviced by those microservices running in those pods, running in those containers, or running on those nodes. And so you need to connect all those layers to each other in order to be able to say, okay, somebody made a change to the Kubernetes cluster's configuration, some CRD was pushed, and that relates to the business service. So that's why we're saying change implies topology, because if you have the change, you still need to relate it to something. And then the question always is like, which change is now the one impacting my service? And then you need to be able to follow those relationships. Now, causal observability is important, but it's becoming more important also as time progresses, because the speed of change and complexity is exponentially increasing. Services like Kubernetes, for example, will redeploy restart pods and just throw new pods up, auto-scaling events and so forth, and remove pods when an issue is occurring. So something that we've heard time and time again is that with like, even if you just have a topology of the current moment is already outdated to when the issue started by the time that you look at it. So an issue starts, Kubernetes is restarting a bunch of pods, is immediately busy trying to remediate the problem by its crude action of restarting pods. It doesn't work. It might even make the situation worse. So at some point, some engineer looks at it, and then the containers that are there and the distribution of containers over nodes is entirely different from the moment that the problem started. And so that really also speaks to the fact that, we need causal observability. We need to be able to reason about cause and effect, but we need to be able to reason about it over time, because speed of change and complexity is exponentially increasing. And then last but not least, when you have topology, you will be able to relate it to all the telemetry that you already have out there. So I have metrics, logs, traces, and those always relate back to a component or a set of components in my topology. And so really what this level of observability does, it enables all causal reasoning, because now you have everything that you had at level 2. So you have your alerts, you have your metrics, you have your logs, you have your traces, but you're able to put that umbrella over it. And what the Superman used to do now can be done by the system. Namely, we can exclude entire branches of metrics, logs, and traces, and we don't even need to look at that. And also, instead of having dashboards where you go to, which you have made a priori, that might be that are hit or miss, we can generate from the impact tree. We can generate from that exactly the right type of metrics and logs and traces that might be interesting for you to look at, as well as understanding where the changes were, so you can actually get back to, here's a change, and after that we see a bunch of problems occurring. So causal reasoning is about root cause analysis, it's about business impact, and in fact it's also about alert storm reduction, because if you are able to track all alerts over your topology, then you see an alert happening somewhere, and then you start to see alerts happening in connected pieces of those topology. It becomes extremely easy to cluster them, and that's actually just follows from the data. So that's something that StackState is also able to do, but really it isn't a super smart algorithm. It's the data that makes it easy to see that. And that's also one more hint that really what we need to be able to do is we need to be able to reason about causes and effects. And in order to do that, we need topology and change. So here's one other way of looking at it. So when you're troubleshooting at level 2, you have on the y-axis here number of involved people, and on the x-axis time. And so you have at some point normal operations, and then at some point an incident happens. Now, at that point in level 2, you can have lots and lots of alerting. So all teams that have something to do with the cause and as well as the effect will get their alerting. So now a lot of people are involved. And then as time progresses, and we are able to expand our analysis, we are able to eliminate also, again, branches of possibilities. And that means like, okay, this team, even though the problem propagated through their part of the stack, their services are working fine. It's below that we need to be. So we can eliminate them. These people will be on standby in case something needs to happen, but they don't need to now also dive into that. And so you see this long curve, where and then after elimination has happened, we can then identify the root cause and start to stabilize the system. And in level 3, the shape of the curve still looks the same, but you don't need to involve that many people anymore, because you understand where the problems originated and you understand the effects of that. So, and everything in between. And means that you can start to alert on cause and impact. And so that doesn't mean that people in between don't need to do anything. They can be just informed. And so that means that you're eliminating a lot of the cost involved in solving the issue. And because you're now also partly able to automate the root cause analysis, especially in, finding the change that led to the failure, and finding the first alerts and so on, that after which an alert storm happened, you're now able to reduce the time. And so you will be able to eliminate a lot of the cost involved in the troubleshooting process. And that's really why causal observability is quite important. And yeah, it's central to our hypothesis. And in the years that I've been working on this, I've seen it clearly again and again that in order to make sense out of large quantities of data in super complex and highly dynamic environments, you need to be able to do causal reasoning. And so really that's what this level is about. Even faster troubleshooting is what you get, less engineers and proactive communication. I think I want to use one more analogy that somebody used at some point. It wasn't me, but I thought it was quite well done. And that's like, looking at Formula One, they do a lot of monitoring of those cars while driving the race. But all that engine that is then under so much pressure is an entirely static system. And that's really what makes Formula One monitoring so much easier than IT monitoring. Because it's not that you have an engine and you can just put in a bunch of instruments to instrument those the different parts of the system, but the system itself is constantly changing. And observability, as it stands with metrics, logs, and traces, give you those deep insights that even with those Formula One engines they have. But you really need to go one step further to really deal with the fact that the engine itself is constantly changing. And that's central to this maturity model. So there's 3 reasons why our vision goes beyond level 3. Getting to level 3 is already a big challenge for the entire market as it stands. But when you're at level 3, we want to still go one level further. And on level 3, you still need to separate the signal from the noise. So you have all those metrics, you have all those logs, you have all those traces, but which one matter? That's pretty hard to determine even with this. And all processes can still be further accelerated with machine assistance, which we'll talk about a little bit later. And the question is, can we eliminate troubleshooting altogether? So you're talking about that curve, and also you guys have put in the poll, we want to be proactive. Can we do that? And simply by having the topology and the changes added on top of the metrics, the logs, and the traces, we're still not there. So level 4, it's about proactive observability with AIOps. And AIOps is really about machine learning and combining that with big data in order to automate IT operations processes. And it says here, this is a quote from Gartner. It's about anomaly detection. And also, interestingly, they put causality determination in there. So that's quite interesting that Gartner would say that indeed. And it's about, the big, when you focus AIOps on observability, because AIOps is actually a little bit larger space in which security is also included, then the question is, how can we prevent issues altogether? Like, can we be proactive? And then we really are getting into a question of, like, is AIOps science fiction? I have to be totally transparent with you, and I actually want to be transparent with you. Like, from all the AIOps solutions that I've seen out there, not one really lives up to its promise. And the reason for that, in my opinion, or in our opinion, I would say, is that we're trying to do something for which we're not ready. So another analogy here is when, like the big goal with self-driving cars, the autopilot, at what point are we ready to do that? Are we ready to do that when a car only has onboard navigation? Can we just create an autopilot by knowing where the car is? So of course not. We need to not only know where the car is, but we also need to have much more data about what's going on in a car. And so right now, I believe in terms of autopilot for cars and assisted driving, we have enough data in order to be able to achieve that dream. But when it comes to AIOps, and actually really preventing issues and maybe even automatically remediating issues, the question is, at what point do you have enough data? And what we're saying is, when you don't have the topology and changes, you don't have enough data. When you do have topology and changes, metrics, logs, and traces combined with the alerts, then you're kind of data complete. Like in algebra, algebra is complete, when you are able to square roots of negative numbers and so on. But then you have your data complete. So at that point, you will be able to do it. But if you try it before that, you're going to be able to spend a lot of time trying to determine things that you should just know. So let me give you a very concrete example. There are event/alert correlation tools out there. I'm not going to name names, but what they will do is they will look at patterns when alert storms happen, where they look at, like, do events happening pretty much at the same time look similar? And they can just use natural language processing to determine whether something looks the same. And if two events look the same and they happen around the same time, then they're probably correlated. And that, in my, like, what we have seen is that doesn't work well at all. And also another way of doing that is, when event X happens, then typically event Y happens, then typically event Z happens. Therefore, we can learn that pattern, and then next time event X happens, we're going to be able to predict that event Z will happen. Those are two applications of AI and machine learning that really aren't very good. Like in the second case, for example, predicting when event X happens, therefore event Z is likely to happen, assumes that the system stays the same. But in fact, when you have a P1 outage, then you're going to try and remediate the root cause. And that means that, event X will not trigger event Z. And when event Z is there, it does not imply event X. And when it comes about, when you're looking at natural language processing, then just two events saying the word database does not mean that they're the same. They're correlated, and we've seen that also a lot, where things that, when you know the topology of your system and you are able to plot those two events on a topology, if you cannot find the path from this event to this event on the topology, then it's silly to even try and correlate these. So you can spend all your AI and machine learning on things that are just fundamentally, you can already know that it's nonsense. And so topology is the context not only for people, but it's also the context for machines, in order to be able to focus their attention on those things that matter. And that's really the key here. Like, you can do predictions of, some service, is going to slow down over time. But if you are unable to relate that to its effects, like what is that going to mean for our customers, then it's unclear whether that is an important prediction or not. And so it's important for AI to have that context too, and that makes that attention can be used. And in that vast amount of data, you can throw a limited amount of compute at your metrics, logs, and data and still get really good results out of that. So even though I've kind of spoken why most companies aren't really ready for AIOps because they're trying to skip that step, or they've not even considered that step of like, hey, how do we even make sense of our data? Still, AIOps should be on your radar. And really, when it comes to separating the signal from the noise, it's a very important tool. So you have things like anomaly detection, really trying to tell you like where should I focus my attention. And we're talking about large volumes, variety, and velocity of data, and those are increasing. So we really need to do something on that front. And that's also what I told you in the beginning, like, even though there are 4 levels, and we find that if we draw a curve through where is everybody at each level, you find a linear curve that I'm going to show to you also soon. That doesn't mean that if you're level 1, you shouldn't be thinking about level 4. And it provides you insights valuable to your business that were unthinkable before. So here, really, at this level is where a lot of magic will happen. But right now, it's not yet happening, at least not. I think we're still before the time where AIOps is really going to make the difference. It's going to drive early and accurate responses. So it's going to also improve causal reasoning, because the topology will give you an understanding of the basic cause and effects of a system. But you can go one step further and start to correlate metrics of dependent components in order to determine the strength of the causality that you have. And also you can do that to the events that happen over time and so on. So there's a lot that can be done in that space to even get better causality. Proactive observability detects anomalies that matter, and eventually we will drive remediation. So here's a summary of all levels. I'm going to tell you to download the Observability Maturity Model. It's in the handout. So if you go on the tab handouts, you will be able to download it. Let's see if it's there. Yep, it's there. And also you can go to our website in case you want it at a later stage. So here's another polling question regarding the various observability levels. Where would you benchmark your organization? So is that at level 1, monitoring, level 2, observability, level 3, causal observability, or level 4, proactive observability, AIOps? So Cody, is the poll up right now? And that's very cool. So here what we can see is that level 1 and 2 are equal in this race, which is kind of nice. And then here you can, when you draw that linear regression line through these 4 levels, you can clearly see what our main hypothesis is, namely that 1, 2, 3, and 4 follow in a nice progression. And that's what we've seen time and time again. So when we look at the market, we can actually see very similar numbers here, where we see that when we ask that question to 543 respondents, apparently, that you see that natural curve. And also, we currently have a detailed observability maturity model assessment in the works. So if you want to participate in that, you can contact us. And that assessment actually tells, it's not a question of where are you at 1, 2, 3, or 4, but it's more of a question of how much maturity do you have on each level. And then the linear curve becomes even more clear. So here's the recap. Growing the practice, driving customer satisfaction with the maturity model. Going from level 1 to level 2 is really about understanding state with metrics, logs, and traces. Open telemetry plays a big role. And level 2 to level 3 is about understanding cause and effect. And then level 3 to 4 is about understanding patterns that will be found by AI. And that's in very short version of the observability maturity model that you will also be able to download and get more detail on. Thank you for listening. So we have a Q&A. I wasn't very fast, so we don't have that much time. But well, then, Cody, take it away.
Let's dive right into them and see how many we can knock out. So what do you find are the biggest challenges organizations struggle with when implementing observability?
Biggest challenges organizations are struggling with. It's quite diverse, but what I do find is that top down, there are typically there's a lack of overall strategy, and what you find is decentralized movements nowadays. And when you look at the market, so you have decentralization. Okay, let's give the DevOps teams the tools, or let's give them the autonomy to pick their own tools. But what you then find is you find an outgrowth and sprawl of different tools happening all over the place. And right now we're in one of those. So I'm seeing a lot of directions happening or movements happening in all directions. And later on, of course, those are going to be centralized more so in new ways. But this decentralization, even though it has all the benefits of autonomy and of empowerment of the different teams, and being able to choose the right tool for the right job, which are important factors, it has the problem of lack of overall strategy. And that's really what I see as the main problem that companies right now have with observability.
Thank you for that. Our next question, how do you keep the topology up to date given the continuous changes happening in a cloud-native IT environment?
Yeah, so there's several strategies there, but really the only, let's say if you put a requirement on that, really you want to be able to get those changes within milliseconds, within seconds at least. You shouldn't be behind far, because those cloud native environments are moving pretty fast. And the good thing about these environments is that they also allow vendors like us to be able to create agents that are able to instrument those environments in real time. So for example, with Kubernetes, our agent sits as a daemon set on each node and is able to use the eBPF kernel module in order to see all the real-time connections that are happening between the different Kubernetes pods. But also the Kubernetes API is able to give us all the changes that happen. And so there is a subscription to all those changes that our Kubernetes Go client has. And as soon as a change happens, those changes flow through Kubernetes right into our system, so that we're able to create that real-time topology. Yep.
Awesome. Well, Lodewijk, it looks like we are at the top of the hour, and I do still need to give away a couple of gift cards. So I do want to just give you one more chance to say anything you'd like to the audience, any parting words, or anything that you feel they need to know before we close out.
Well, most importantly, I mean, I've not met anybody personally tonight, or in your morning, I guess. But if anybody wants to reach out to me, just contact StackState, ask for me, and I'm more than happy to have a conversation with you on any question that you may have. Yeah, that's important for me to have said. So thank you for listening.
Well, thank you so much for joining us. We really appreciate the time and effort that goes into putting these presentations together. So thank you, Lodewijk. So
Thank you.
I would love to remind our audience that this session was recorded. So following this program, you'll receive an email with a link to access that recording on demand. You can also find this living on the DevOps website at devops.com/webinars, and just be sure to look in the on-demand section. So we do have 4 $25 Amazon gift cards to give out. Our 4 winners are Certain R, Louise P, George's R, and Sarah M. So to our 4 winners, congratulations. Please keep an eye on your email inbox to claim that gift card. But if you do not see that email, just check your spam folder. I would like to thank StackState for sponsoring today's program. And to our audience, thank you so much for joining us today. We do ask for 1 extra moment of your time for a brief survey that will pop up as soon as we close out. But otherwise, we hope to see everyone at an upcoming Techstrong Learning program. Everyone have a great rest of your day.